Welcome. We're now going to be talking about part 3 of our module on Gang of 4 and POSA 1 patterns as they relate to concurrent and network software. The previous part described the use of the proxy pattern in order to shield the client application, in this case an activity, from where the actual object resided, whether it be in the same address space, co-located, or remote in a separate process. Now, we're going to be fleshing out this example to use a related pattern called the broker. Just to recap quickly, the example we're using is still the same. We have an activity which responds when a user clicks a button to provide a URL, which is then requested by the activity by invoking a method on a proxy to talk to an object that lives in a download service. That object turns around and uses a GET request to request a web server to download the image content. That content is stored in the file system along with some metadata that resides in a content provider. And the Uniform Resource Indicator, or URI, is then returned back to the activity, which displays the content after it's been downloaded. We're now going to go and talk about how the broker pattern figures into this particular example. So what's the context for this? Well, it's often the case when you're building networked and concurrent systems that you have multiple objects which may reside in different address spaces. Not always, but may. And so what you'd like to be able to do is access these objects both synchronously, in other words, the client blocks till the request is done, or asynchronously, where the client invokes the request and then comes back sometime later to pick up the result. So what are some of the problems that arise when we build systems in this particular manner? Well, one of the problems is that we really don't want application developers to have to wrestle with low-level message passing details. This is really what motivates the proxy pattern. We don't want them to have to think about marshalling, demarshalling, framing, demultiplexing, all the other kinds of things, because that's really the kind of activity that is full of so-called accidental complexity. Application developers don't need to know this stuff. It really should be pushed down into some lower-level infrastructure framework to do the work for us. Another problem we want to have here is we want to shield the application developers from the computing diversity that arises when you build networked systems. For example, in Android, you can have activities and services that are implemented in Java, in C, and in C++. And we'd like to make it possible for these different activities and services to talk to each other in those different languages without requiring the application developers to figure out how to do inter-language interoperability. In other environments, not Android per se, but in other environments, we may have different operating systems that are talking to each other. You may have clients running on Windows talking to servers written in Linux. You may end up running over different networking protocols. In Android's case, we're talking over the binder driver through a loopback inter-process communication mechanism baked into the Linux kernel. In other environments, we might be talking across TCP/IP or some other kind of networking protocol. And once again, the application developers should not have to worry about these kinds of issues. This level of heterogeneity really should be somebody else's concern, not the application developer's concern. And of course, we'd also like to shield application developers from some of the inherent complexities of concurrent and networked systems. For example, partial failure, the fact that different pieces of the system may fail independently or may hang for some period of time before resuming. There may also be issues with latency. If you talk over a slow connection or you send a lot of data over a connection, it can take a while. And you don't necessarily want the application developers to have to keep track of all the details of these latency-related issues. There are also these days many issues pertaining to secure coding, security mechanisms, security protocols. And the application developers shouldn't have to be concerned with those details. Those things should be somebody else's concern, provided by other mechanisms in the system. If you take a look at the URL on the screen, I've written a number of papers and articles that talk about some of the inherent and accidental complexity of concurrent and network software that you might want to take more of a look at. So what's a solution? Well, one way to solve this problem is to separate out the system communication functionality, which is really an infrastructure concern, from the application functionality that actually handles the business logic. And the way to do this is to provide a broker that isolates the application part from the communication-related concerns. There's a variety of different ways to do this. One way to do this on Android is to implement things as follows. You implement a so-called binder object, which is capable of being accessed from another address space. You then provide a proxy to that to another application in a different address space, an activity or another service. When the client in that activity or service invokes a method on the proxy, the underlying binder mechanism from Android, which is playing the role of the broker, communicates with the object across the process address space boundaries. And in Android's case, there's a few other moving parts. There's something called a stub, which is automatically generated from the AIDL compiler. And that's what's used as an adapter to link the incoming request coming up from the binder to the actual remote object, which does the work and then potentially returns a result. Note, by the way, that even in this simple example so far, we've got a number of patterns working together. We're describing something called the broker pattern, and we're also talking about things like proxy and how they relate to each other, illustrating once again that patterns are never islands. They almost always interact. Also note that Android makes it possible to provide both synchronous and asynchronous communication via their broker mechanism. We'll be focusing on the synchronous form here, but there are other patterns, other techniques for providing asynchronous communication. So as with proxy, the broker pattern is also something that's been around for a long time. And the particular arrangement of roles and responsibilities that we see in Android are really just manifestations of these deeper, more fundamental recurring design structures and behaviors. The broker pattern we're talking about here comes from a couple of sources, starting initially with the POSA 1 book, where it's described as an architectural pattern. The intent of the broker pattern is to connect clients with remote objects by mediating invocations from clients to these remote objects while encapsulating or shielding the objects and the clients from the low-level inter-process communication and networking details. So you typically want to use this pattern in circumstances where it's not appropriate for application developers to wrestle with a lot of the low-level communication concerns. Things like connection management, data transfer, concurrency, synchronization, various forms of fault tolerance, being able to manage end-to-end quality of service, timing properties, transactional properties, and just in general encapsulating all this low-level mechanism for being able to do inter-process communication within a device or across devices. The structure of the broker pattern is typically arranged as follows, as shown in this diagram. You have a proxy that the client invokes a method on. As we discussed with the proxy pattern, that method on the proxy converts the native parameters into a message containing other information necessary to ship this particular message from one address space to another. And it's the responsibility of the broker libraries, which are typically linked in to both the client and the server, to perform the connection management, data transfer, concurrency, synchronization, demultiplexing, and so on, to move the message across address spaces. Once the message has been received on the other side, then it's reconstituted through a sequence of steps we'll talk about later, and some type of adapter is then used to convert the message back into a method call on the remote object. And of course, if there's a return value or return parameters, they go back the opposite direction, doing more or less the same set of steps in an inverse manner. Here's an example of some of the dynamics of the pattern. You can see that the object that wants to be accessed via the broker registers itself, and then somehow through a naming service, a location service, a client discovers the address or the object reference to this object. The object invokes the operation, some type of connection is typically set up, and the rest of the process takes place as we just described, with the broker doing the bulk of the heavy lifting to shield the application from the low-level communication concerns. Let's take a look and see how we might implement this pattern in Android. Android has this binder framework which has a number of canonical steps in order to carry out communication from client to server. What we typically do is we first have some activity called bind service, passing in information on which service we want to connect to or bind to. The bind service call talks to the binder, which checks to see if the remote service process is already running. So for example, in our case, we have the download activity invoke the bind service call, which turns out to call the download, it calls the binder, which in turn launches the download service process if it's not already running. And it then goes and calls a method on the service called onBind. OnBind turns around and returns an object reference to an object that implements the interface in question. In this particular case, it's the iDownloadImage interface. And that gets sent back to the client process, where it comes back through a callback mechanism known as the onServiceConnect hook method on something called a service connection. The proxy that comes back is downcast and stored into a local data member, which is really the proxy at this point. And when the activity invokes the download image method on the proxy, that in turn triggers a call back to the corresponding method on the iDownloadImage object. And that object's method runs in a separate thread of control, does the work to download the image from the web server, and then it returns a URI back to the client activity, also using the binder. So one of the key things to note with this example is that there's a number of other patterns involved. We see proxy being used to shield the client from where the actual object resides. We see the activator pattern that we'll talk about later used to launch the download service process on demand. We see adapter, which is another pattern that's used to connect back up the up call from the binder up to the iDownload object, and so on. So the patterns work together, and we'll talk more about that later. Let's take a look at some of the code that implements pieces of this example. So here we have the activity for downloading, and here's the proxy object, which we call mDownloader. Here is the hook method that's called back to return the proxy from the server process running the download service back to the download activity. And here's where the download activity uses the proxy to invoke the download image method, which will then, of course, eventually be delivered over to the server process and the download service binder object. Notice how the use of the broker in Android shields the application developer from many of the low-level details of communication. You don't really have to know a lot about how the mechanisms take place under the hood to transmit information back and forth. That's done for you by Android. Here's a little bit of the code that's implemented on the server side. This is the download service. And as you can see, when its onBind hook method gets called back by the Android binder framework, it returns the object reference for the download binder object, which is what actually implements this particular service. And that comes back over to the client through the methods we just saw. And then when a client invokes the download image method through the proxy, this particular download image implementation method is dispatched by the binder framework as an upcall through the stub to go ahead and do the actual work of getting the image content from the web server and returning it back as a URI. Once again, notice how the implementation of iDownloadImage is isolated from communication level concerns. Those kinds of things are sort of pushed down into the framework. You as an application developer don't have to know how they work. You just have to know what hook methods get called back by the binder framework, implementing the broker pattern to do the job. Now, Android is, of course, not the only system that implements the broker pattern. In fact, you could argue that a lot of the steps that Android requires of application developers are a little bit convoluted and require fairly deep knowledge of interactions and callbacks to make sense. Another more common example of the broker pattern is something called CORBA, which is the Common Object Request Broker Architecture. Broker's the middle name in CORBA. CORBA shields applications from many other details that Android tends to expose in a bit more detail. With CORBA, you get an object reference, much like the proxy that comes back as an interface from Android, and a client application invokes a method on this object reference that uses the proxy pattern to convert the method to a message, passes it off to something called an orb core, which does the actual low-level broker communication across address spaces. When that request message shows up on the server's orb core, there's several levels of demultiplexing to convert that message back into the appropriate object it's targeted at, back into the appropriate upcall onto the appropriate method in the appropriate object implementation. And once again, if this is a two-way call, the same sort of process takes place going back to return the result back to the client. One of the things that CORBA does that goes even further than the Android binder mechanism is it shields the application developers from even more diversity. So for example, not only can you have different programming languages, but you can also run on different operating systems, you can run over different protocols, you can have lots of different hardware involved, and CORBA shields you from all those details. We'll talk more about CORBA and brokers later on in the course. So what are some of the consequences of using broker? Well, one of the key things you get is location independence. The applications don't really know, don't really care where their objects reside. The broker takes care of that. You also have a nice separation of concerns. So all these low-level, tedious and error-prone details of concurrent and networked programming are handled for you by the broker. An application can focus mostly on its business logic. And of course, if you get the right kind of broker, you can get more portability, more reusability, more modularity, and so on, which is also often a win, especially in very heterogeneous environments. There are some downsides, of course. If your broker is not implemented well, then every application will incur additional overhead, which may make it difficult to meet its quality of service requirements. You may miss deadlines. You may be unable to give people the appropriate responsiveness they might have come to expect from other types of solutions. Another issue is if you implement a broker that only supports synchronous communication, you'll end up with a lot of threads that are running around in the application on the client side, which can be tricky to debug and understand. There's a number of implementation considerations when you go to reify or instantiate the broker pattern. One of the big questions is, do you put time into optimizing interactions between clients and objects that happen to be co-located in the same address space? Better implementations of the broker pattern typically optimize these co-located paths because it allows you to change your mind about system partitioning architecturally very late in the design cycle, even at runtime. Other considerations: do you support both synchronous and asynchronous communication? Once again, better broker implementations typically support both because it gives more flexibility to architects who are trying to build their solutions in the most appropriate and efficient and easy to understand way. Other considerations: do you allow your broker to run across different transport protocols? Android's broker is really hard-coded to work over top of the binder IPC mechanism and the binder driver that's part of the Linux kernel on Android. CORBA, in contrast, provides ways of plugging in different kinds of protocols so you can run over a wider variety of different transports without changing the client and server experience. There's also many issues from an implementation point of view in terms of how do you strategize certain concerns or implementations or mechanisms of the broker itself. Do you support multiple concurrency models? Do you support multiple different strategies for synchronization, for fault tolerance, for connection management, for security, and so on? We'll cover these issues a little later in the course when we talk about pattern relationships and pattern sequences and pattern languages. There are lots of examples of brokers in practice. The best known ones probably come from the distributed object computing middleware family of solutions, CORBA, Java RMI, back in the older days, things like DCE, which is more of a procedural approach to this, and so on. And of course, in a more modern way, the various frameworks we see with Android that provide local inter-process communication within a device. Some interesting place to look for additional information about Broker is a revisited version of the Broker pattern from the original POSA 1 book. The authors went back a number of years later and took a look at some of the literature that had been produced between the time they wrote their initial description of Broker in the mid-90s and came up with a revised version that tries to capture more of the design issues, more of the forces, provide different approaches to different implementation techniques, and so on. So to summarize this particular section, the Broker pattern is very widely used in concurrent and network software. There are lots and lots of open source implementations of brokers that you can download and learn from and use on your projects. Many of these are not just for learning, but they're also industrial strength that are widely used in quite a wide range of domains. Some of the better known ones are the ACE orb called DAO, which is a C++ implementation of CORBA. JackOrb, which is an implementation of CORBA written in Java. And it's also important to realize that Broker is not ultimately just an architectural pattern. It's really a pattern language that groups together many other patterns in order to provide the isolating communication mechanisms that shield client applications from the details of the underlying networks and inter-process communication mechanisms. There's even a book that describes Broker as a pattern language and a number of patterns related to remoting. And we'll be talking later in the course about some of the patterns, some of the pattern sequences that make up the Broker pattern.